Tonight we're going to be talking about a little red planet who has some really interesting secrets stored away in its rocks, and we're going to wait for Ben to tell us all about what those secrets are. For now, I'm going to just introduce myself. My name is Dr. Annie Quinney. I am a professor in the Department of Earth, Energy, and Environment at the University of Calgary. I'm so thrilled you are here with us tonight, whether you're here in person or you're joining us online. We're going to invite you to ask lots of questions at the end. So at the end of the talk, we'll bring around a mic for everybody in the room. And if you're joining us online, you can send your questions to our email at scievents@ucalgary.ca, and I will remember to give you that email again at the end of the talk after Ben's all done. So we're going to begin this evening by acknowledging the land on which we gather. The University of Calgary, located in the heart of southern Alberta, both acknowledges and pays tribute to the traditional territories of the peoples of Treaty 7, which include the Blackfoot Confederacy, comprised of the Siksika, the Piikani, and the Kainai First Nations, the Tsuut'ina First Nation, and the Stoney Nakoda, including Chiniki, Bearspaw, and Goodstoney First Nations. The city of Calgary is also home to the Métis Nation within Alberta, including Nose Hill Métis District 5 and Elbow Métis District 6. We can't go to our talk right away without thanking our sponsors. So a big thank you to the University of Calgary Alumni Association. You may have seen their booth out front tonight. As a University of Calgary alum, you may not know this, but you actually have access to a whole bunch of benefits even after you graduate. So there are events and there are field trips, and there's even one coming up relatively soon. So that's the Grow Your Career, Get Hired series. If you have any questions about the benefits of being an alum from the U of C, I invite you to go talk to a different Ben just at the alumni booth outside in the lobby. I also really want to thank the Gallagher family for sponsoring this event. They have been long-term sponsors of EARTHx, and we are so grateful because they allow us to bring science to the community. They allow us to bring EARTHx and Mars to events like this. So we are very grateful to the Gallaghers. Tonight, of course, our topic is Mars. That's why we're all excited to be here. Of course, this is the little red planet that has no life, at least not today. What we do know about Mars is that its surface is shaped by water, its chemistry records change, and there are clues on the planet that tell us that the surface was very different in the past than it is today. Here to share the story of Martian geology and what rocks can tell us about the potential for life on other planets is Dr. Ben Tutolo. And you may have heard Ben's name before because he was recently on the cover of Science magazine. And we are really proud of Dr. Ben Tutolo because he's actually a professor in the Department of Earth, Energy, and Environment at the University of Calgary. And I'm especially excited and lucky to have Dr. Tutolo just down the hallway from me because I have a lot of space questions. And it turns out after this talk, I'm going to have a lot more. So Ben, I will be bugging you tomorrow. You can expect me in your office. Please welcome Ben to the stage for his talk, Exploring Martian Geology for Potential Signs of Life.
Thanks, Annie. It's always nice to hear a colleague say nice things, and it was lovely to hear that intro. And thanks, everyone, for coming. I'm talking about one of my favorite subjects tonight, the history of Mars and its potential to have originated life, and also how we can study Mars to understand how our own planet originated and has sustained habitable conditions and life over much of its history. So I'm going to start at the beginning, so you can imagine around 4.5 billion years ago, our solar system formed, and it formed as a big cloud of dust and elements circulating slowly, forming into the planets and planetesimals that ultimately became our planet, Earth and Mars and all of the other planets in our solar system. And this history of our solar system ultimately gave rise to one habitable or habited planet that we know of, which is Earth. So we have a concept known as the habitable zone. The habitable zone being defined by the area that is a certain distance from its star in such a place that it can be just right to maintain liquid water over geologic timescales on its surface, and therefore be habitable and potentially inhabited. So habitability is this concept that we use in astrobiology and planetary science to try and understand and put constraints on planets and their potential to have originated life, but it's based entirely on our own life form that we know from Earth. So we have this N of 1, Earth, that tells us that you need liquid water to maintain life. And so you can be on the inside edge of the habitable zone and be potentially too hot. And then the outside edge, so beyond Earth's orbit, potentially including Mars now, and be too cold. So examples of this are planets like Venus. So this is actually a picture of Earth, but the idea here is that you can be so close to the sun that your planet is too hot. And so on the surface of Venus today, you can actually melt lead. That's how hot it is. And you can learn a lot more about that at the next EARTHx, which Annie will talk about a little bit later on. So you can be too hot. You can be just right. So you can be Earth. So if you think about Earth, habitable environments, many of us can imagine sitting on a nice sunny beach here on Earth. And you can probably, if you are a little bit creative in your imagination, imagine more or less this same picture having existed through much of Earth's history, where you have a beach, sand weathering onto a beach, and a big body of water existing throughout our history. So for around the past 4.5 billion years. And potentially at some point, Mars would have looked like this as well. And that's what I want to talk about today. But ultimately, you can be too far out of the habitable zone and be too cold, planets like Saskatchewan. And in this case, you can be such that the insolent solar radiation is actually too low to keep your planet warm. So thinking about Earth, sitting right there in this habitable zone, this place where liquid water can exist and apparently has existed for 4.5 billion years or around 4 billion years. And we can think about the history of Mars in this context as well, because we know Earth originated life at some point in its history, and we're wondering exactly whether that same process would have happened on Mars. So Earth 4 billion years ago was a very different place in many ways. So our moon was young. As our moon was actually formed shortly after the formation of Earth, the moon was really, really close, actually. So it would have covered much of the horizon if we were looking off into the sky. And slowly through time, the moon has been getting further and further away from Earth. If you don't know, the reason that we actually know this is that Apollo astronauts put mirrors on the moon, and we were able to shine a laser up to the moon, and we could see that through time, through precise measurements, that the moon is getting further and further away. And if we wind that back to 4 billion years ago, we know that the moon must have been much closer than it is today. And from Mars, we've been studying Mars from orbit and now from the ground in situ using rovers for many decades. And so we know, based on the history of Mars and physical modeling and geochemical modeling, that we can actually look at its history. So this is Gale Crater. This is where the Perseverance rover is located on Mars. And people have thought, because there's basically a large delta there in Gale Crater, that this must have been a river that transported sediments into the crater, and it slowly settled and became the rocks that now Perseverance rover is exploring today. But as we all know, Mars today is a very different place. It's cold and dry. So very cold. I can show you this because these are actual temperature measurements that have been taken by the Curiosity rover over the last week. So up until January 23rd here in this particular set of data. And you can see the highs are not so bad. They're on the order of 5 to 10 degrees daily, at least this time of year. We're in basically the middle of the spring on Mars, where Curiosity is. But the lows are low, right? So the lows that we see here are on the order of minus 70 degrees Celsius. So even though we complain about how cold it gets here in Alberta and also in Saskatchewan and Manitoba, you can imagine that actually this place is much less habitable because it gets much, much colder than we can even imagine getting here in Canada. And Mars is also very dry. So this is an actual video of a dust devil that was taken by the Curiosity rover on Mars. And you could see basically these windstorms on Mars are picking up dust because the place is covered in dust. because it's so dry and it picks up the dust and then forms these little dust devils. Okay, so we know two things with certainty. Mars was once warm and wet. It had enough warmth, enough heat in its atmosphere to actually, or enough heat on its surface to actually stabilize liquid water. And two, today it's cold and dry. So I'm sure that many of you have thought about this, the so-called scientific method. So I wanted to lay the presentation out tonight in terms of the scientific method, which we were all asked to learn in school. So the first step in the scientific method is a phenomenon that requires explanation. In this case, Mars used to be warm and wet, but it's now cold and dry, right? Very simple observation. We have clear evidence that there was rivers flowing on the planet, that minerals that require water to be made are observable on the planet, but now no such process is happening. Two, let's come up with a hypothesis. Mars used to have a much stronger CO2 greenhouse than it does today. So those of us living in the world these days knows that CO2 is actually causing our planet to get warmer, the surface of our planet to get warmer, as anthropogenic CO2 is emitted into the atmosphere faster than the Earth can take it up. Our planet is warming, right? So we've increased temperatures by on the order of 1.5 degrees since the beginning of the Industrial Revolution, and it's not yet showing signs of stopping. And Mars and Earth in this early time, 4 billion years ago, whenever the planets were just young enough to host the liquid water that we see on Mars, the sun, this is an animation of the sun taken recently, actually the sun was much less bright than it is today. So about 4.5 billion years ago, it was 30% less bright than it is today. And through time, it has been getting brighter and brighter and bigger, such that in some number of millions or billions of years, the sun will eventually overtake Earth. It'll get so big, it will actually burn up our planet. Okay, so the greenhouse works on Mars the same way it does on Earth. So if the sun is giving radiation heat off to the planet, the sun rays will get trapped in its greenhouse. This is what's happening on Earth and stuck in there. And Mars, in order to do the same thing, because it's further away, because the early sun would have been much colder, it would have needed, in principle, a much thicker CO2 greenhouse to trap all of that heat. And the way I like to explain this, at least to school children, and I'm sure many of you can think about this today, is the fact that you could park your car outside on a hot summer's day, and even though it's warm outside, you go in that car, it's way hotter than it is outside. It's because it has this greenhouse effect. It's trapping the radiative heat that goes into the car, and it's not letting it go back out, so it heats up kind of like an oven. Okay, and we know that planets need greenhouses to be warm. And how do we know that? If we actually did a very simple calculation of what temperature Earth would be if it had no CO2 greenhouse at all, it will be about minus 18 degrees Celsius. So this planet, the planet that we know is habitable, right, has sustained life for around 4 billion years now, has only been able to do that because it had carbon dioxide in its atmosphere. If it didn't, it would be cold. It would be a snowball, like the snowball Earth animation here. Okay, so again, our hypothesis here is that Mars used to have a much stronger CO2 greenhouse than it does today. So how are we going to move on with our scientific questioning of this? We have to design an experiment. Okay, the experiment that we can design is to send spacecraft to Mars to examine ancient rocks. And spacecraft here is used in a direct way. So I mean spacecraft that can be orbiting the planet. So we've done lots of investigations from satellites that we've sent to Mars. But we could also choose specific places on the surface of Mars to investigate in more detail using rovers. So here is a map of all of the lakes that have been identified in orbital data from Mars. And you can see there is something interesting happening in this data set, that most of the lakes, or most of the evidence for lakes that we have, are concentrated in more or less the southern hemisphere, and much of the northern hemisphere is quite smooth. So Mars has this crustal dichotomy. It's thought that those craters, the places where the lakes formed in the southern hemisphere, are much older than the northern hemisphere. But we're still not entirely sure what caused that. Some folks hypothesize that the northern part of the planet would be one gigantic ocean at some point in time, although the jury is still out on that. Okay, so each one of these dots here, the blue, black, and red dots, is a place where we've looked in the orbital data closely and determined that there are signs that there used to be a lake there. What are we looking for? We're looking for potentially signs of a river going into the crater, a river flowing out of the crater, or just the erosion of walls on the crater. Or also, we can also look at mineralogy using spectroscopic techniques and look at minerals that exist there, and they would be consistent with the formation of minerals that form under liquid water. Okay, so we could take this data and we can say, all right, so I want to test my hypothesis that Mars used to have a CO2-rich greenhouse by looking for carbonate minerals, minerals that contain carbon that used to be in the atmosphere as CO2, but has now been deposited as carbonate. So we can look, and here's what we find. Those 5 dots are the only places on the entire planet where carbonates were observed from orbit, or however many there are, a handful of dots. So we looked from orbit and we came up basically with no good answer. So we're confident that all of the data has been processed to its fullest, that we're not missing anything in the data as acquired. But if we look closely at the data, we can say that there's nowhere near enough carbon in these handful of deposits to potentially account for the amount of CO2 that would have been needed in the ancient atmosphere to warm the planet. So we're faced with a problem here, right? We have all of this abundant evidence for liquid water, so rivers and lakes all covering the surface, but we have no good idea of how actually that planet stayed warm enough for those things to exist. And this has been a big question for a long time in the history of Mars, the missing carbon paradox. Okay, so what else can we do? Instead of just searching from orbit, we can send rovers on the ground to these lakes, these lake beds, in order to examine the minerals and chemistry of those lake deposits. So you're probably familiar with, and we have a model of it over here, the Spirit rover, which was sent in the early 2000s. It was part of the Mars exploration rovers, so that Spirit and Opportunity were sent together at the same time. It investigated Gale Crater, which hosted an ancient lake. Curiosity, which is the rover team that I'm going to focus on today and the data that I'm going to focus on today. And Perseverance was sent to Jezero Crater on Mars. And Perseverance, as you might, if you're very slyly looking at the green dots on the previous slide, and this one, Perseverance actually landed in one of those places where carbonates were observed from orbit. And those data are just being published now, even though Perseverance has been there for quite some time. All right, but I'm going to focus on Curiosity, not only because it's the team I'm on, but also because it was objectively the better rover of the ones that have been there. And I can explain why. It actually has the ability to do all of its analyses on the planet, right? It doesn't need to bring samples back to Earth, which is how Perseverance was designed. It actually has a roving laboratory on board. So here is Curiosity in the test bed at the Jet Propulsion Laboratory in California. So you can see it is a substantial unit, right? It is large. It is about the size of an SUV. So these people that are standing there, you can see that at least the RTG part of the back of the rover is about as tall as a person, and the mast cam in the front is approximately, eye level for a human, which means again that it's basically made to be a roving field geologist, but a roving field geologist that can also do its chemical and mineralogical analyses while it's out in the field. And I'll just point out quickly here, the letters that you see, the holes that you see in the wheel there on the rover are actually Morse code, and they're spelling out the letters JPL in the dust as Curiosity continually drives through the rover. And that's because people from JPL are very, very proud of their achievement, and they'd like to write their name all over the planet. Okay, so here's the rover in its instrumentation package. It's got quite a lot going on. I'm not going to get into all of the different instruments. I'll just talk about a few of them, the ones that I'll focus on. One is the chemistry and camera instrument. That's the one that's firing the laser at the rock there. Basically, this instrument has the ability to turn rocks into plasma. We take a picture of the plasma. We can say what that rock was made up of chemically. It's a pretty amazing reconnaissance instrument. The chemistry and mineralogy instrument, that's the team that I work the most closely with as part of the Curiosity rover team. that is the only X-ray diffractometer that's ever been sent outside of Earth. So that particular instrument has the ability to determine the mineralogical composition of rocks on Mars. And the last one that I'll point out, because we are in Canada, is the APXS instrument, which was developed in Ontario and was funded by the Canadian Space Agency and is actually able to measure the chemistry of rocks as we move. And yeah, a lot of the pictures that I'll be showing today were actually taken by the Mastcam imaging instrument as well, which you can see on the mast up there. Okay, so the rover was launched in 2012 and ultimately was delivered to the planet via this sky crane maneuver, which is a pretty exceptionally ambitious process that worked so well they actually used it again on the Perseverance rover around a decade later. So Curiosity landed in the crater. Its sky crane went off to go dispose of itself elsewhere, and then we were ready to go. And this is in 2012. And it landed in Gale Crater. So Gale Crater is a pretty interesting place on Mars. It is a 5-kilometer tall stack of sedimentary rocks. So you can imagine, those of you that are at least familiar with the earth sciences, we can use sedimentary rocks to say something about the history of our oceans here on Earth. That's why we sent Curiosity to Gale Crater, to say something about the history of water on Mars. So these rocks were deposited by water and were lithified by minerals that came out of the water. And by examining those rocks, we can try and understand and interpret the history of liquid water on Mars. And so you can see this is a really lovely photo taken early on in the mission. And as we've gone up and up in height throughout this sedimentary stack, we've learned lots and lots about the history of Mars. So once the rover got there, so it landed here in the Murray Formation at the base of the crater, a nice flat smooth area to land, again via the sky crane. We started the mission operations, and the way the mission operation works is like this. So basically, whenever it's nighttime on Mars, the rover is sleeping and it sends a signal up through the deep space network, which usually involves linking through a satellite that's roving around or orbiting around Mars, back to Earth, which is then captured by a satellite dish here on Earth. And then that goes through the Jet Propulsion Laboratory computers, which we all have to securely log into. And from there, we can actually analyze the data. So as a team, we all then go process the data, analyze it, discuss it, talk about what it means and what we're going to do for our next steps. So that we basically have a day to get through that data. And then by the end of the day, we have to have an idea for what we're going to do on the next day and the next day. And so this has been going on for a really long time now, over 13 years now. And as time has gone on, right, we have this constant fire hose of data, which has been able to continue to provide new discoveries each and every day. And so just to provide some context or some insight to what we're doing, so this is how the mission works. So the fact that Earth is rotating around the sun, what we know as 1 year, basically, Mars takes around 2 years, 2 Earth years to rotate around the sun. What that means is that at some times, we're at complete opposite sides of the sun. So we've just come out of one of this. We call this solar conjunction. We don't do any work with the rover during this time. We actually ask the rover to stand down and go to sleep and measure things like wind speed and temperature, but not do any driving. Because if we try to send these commands to the rover through the sun, they will get corrupted and we could end up having something like drive off the cliff rover, and we try not to do that. So during this time, which we've just come out of last week, we all either take a vacation. This year it coincided nicely with the Christmas vacation, and we all wait for our rover to come back into connection with us. And so whenever that happens, like we are right now, we begin to collect data again. All right. So here we are. We've sent our spacecraft to Mars to examine ancient rocks. And the hypothesis, or so the prediction that we would make based on our understanding is that the Mars rocks should be full of carbonate minerals, right? We looked in the orbit. We weren't able to identify more than a handful of spots where there were carbonate minerals. But we figure when we get there with a rover that can analyze minerals, if for the first time we can quantitatively determine how much of minerals are there, this is going to be our opportunity to actually determine whether there's signs of an ancient atmosphere in rocks on Mars. So there's the rover. This is, I believe, the last selfie that the rover will ever take. It was taken now a number of years ago. But you can see the rover is a very capable field geologist. It is able to do beautiful imaging like this, but also you might see down right within arm's reach of the rover there is a drill hole where the rover was actually able to drill the surface of Mars, again, to get these data for mineralogy of the rocks. Okay, and this video so again, drilling into the surface. We're able to do that. Actually, that drill is sadly a failed drill hole. We were actually not able to get the sample out of that drill hole. But just to show you the types of things that we see with the rover, this particular interval, we're seeing these wave-like formations, these ripples, which are consistent with waves forming in a shallow lake. Depending on which part of the team you're on, whether you're on the French or the American side of the team or Canadian, we were calling those things either baguettes or sausages. But you can see as they weather out, they look baguette or sausagey as they're sitting there. But ultimately what they are ripples that get preserved in the rock. And if we go and look directly head on into them, which I'll show in a second, we can really see the fact that those are waves with peaks and troughs that have actually been lithified and preserved as rocks in the sediments of Gale Crater. Okay, so again, looking closely, this is a very nice image. You can see about 3 centimeters is how big these ripples are. And the ripples, again, are very consistent with shallow water that could not have had ice on the surface because the wind needs to be blowing the water back and forth. And it must be waves basically lapping on a beach. Very much like we've all seen something like this when we've been walking either at the beach, at the ocean, or at lakes here on Earth. Very much like this, where you can imagine, again, ripples forming as waves go in and out from the shallow lake. So again, the picture that has been drawn here, and this is an artist depiction, is that Gale Crater at one point was a very habitable ancient lake with no ice on, right? And actually, some evidence that we have suggests that it was actually quite deep, right? A place where sediments were settling into deep water as they flowed into the crater. And so you can even imagine potentially putting up your lawn chair there and having a nice cocktail and enjoying your day. I mean, don't mind the lack of oxygen or anything like that, but otherwise it could be a really nice place to go. Okay, so we've seen clear evidence, right? We've seen these ripples. There's all kinds of things, features that we've seen that must have been formed via flowing liquid water on the surface of Mars. The issue is, how did that come to be? How did the atmosphere potentially stabilize that liquid water? Okay, so here is Curiosity. The way that it unstows its arm is being shown here, and we can unstow the arm actually and get our drill off the head of the arm. And as the drill again enters into the surface, it taps to do a hardness test, and then it will drill into the surface. And then once we've got the sample up into the drill stem, we actually are able to then bring the arm up over the top of the rover and empty that powder into the belly of the rover. Once it's in the belly of the rover, we can use this amazing chemistry and mineralogy, or Chemin X-ray diffractometer. This is a example of that powder going into a cell on the rover, us shining an X-ray through the sample, a beam of X-rays through the sample. And based on the angle at which they diffract around that central beam, we can say something about the minerals that are in that sample. And specifically, we can quantitatively determine how much of each mineral is in the sample. So we have no doubt, based on this gold standard technique for measuring the mineralogy of Martian samples, that every drill sample that we have is analyzed to its fullest extent possible. So if we look for carbonate minerals in those samples, we can be confident whether it's there or not, based on these data. Okay, so over 45 samples had been drilled 10 years into the mission, and not a single one showed any evidence of carbonates. We were at a bit of a crossroads. So the team had more or less determined, well, atmospheric modelers must be missing something. We must not understand something about the history of Mars, because we're at this place where we have drilled through rocks that must have been laid down by liquid water, must have been laid down underneath a carbon dioxide-rich atmosphere. But we still have not yet seen any evidence that that carbon dioxide was dissolving into the water and making minerals. So 45 samples, 10 years, no carbonates. Right, so the result, we have this prediction and we can come up with the result. There's no carbonates, right? So then our hypothesis has been refuted, right? And indeed, this was published by the team. Early Mars didn't have enough CO2 to keep liquid water, Curiosity finds, right? Liquid water on Mars' surface, but not enough CO2 above to keep it there. So the cognitive dissonance here is real, right? We know from atmospheric models that there must have been CO2 in the atmosphere. We know there's water, but the evidence on the ground is telling us that there was not enough CO2 in the atmosphere to keep the liquid water, right? So those two things cannot both be true, but we're, as a team, saying they must be true, right? Because that's what we observe. Okay, so that's where I come in. So you can see this was published in February 2017. July 2017, I started here at the University of Calgary as an assistant professor. I actually had to get special permission from the dean at the time to go on this field trip to Mount Etna volcano. It was more or less the week after I started. I landed here in Calgary, moved my wife and daughter into our new house and said, see ya, I'm going to Italy to drink wine with some friends, right? And I did. It was lovely. And it was for the Deep Carbon Observatory, which was this 10-year initiative founded by the Sloan Foundation. And the goal of that workshop was basically a bunch of people like me, assistant professors, people that have just started in their career in science, to come up with big questions. Like, what are the things we want to answer as scientists over the coming decades? And I knew effectively nothing about Mars at the time. But one thing I said, I can remember saying it while drinking espresso, sitting on the balcony of our lovely hotel there in Sicily, saying, you know, where are the missing carbonates on Mars? I had just seen this paper from Bristow and others that had been published that said, somehow there was not enough CO2 in the atmosphere, but there was still liquid water. What gives, right? And I asked my colleagues, you know, how are we going to answer this question? Okay, but as an assistant professor, I had a million things to do. I had to teach my first classes, get my lab started, right? And so this kind of went on the back burner. And you could fast forward to 2021, and I got this photo actually from a Zoom lecture that I was giving on the day that I learned that I became a Curiosity rover team member. So I wrote a proposal in 2021 to be part of the Curiosity rover team and ultimately was selected to be part of the team. So fast forward to 2021, I'm actually thinking about these problems now. I'm almost, I think at this time I had been promoted to associate professor, and I was trying now to really dig into some big, serious questions. So that's how I joined the team, and that's sort of my history of Mars rover science. And just like everything else in my life, I stumbled into a wonderful mission at a wonderfully opportunistic time. So right after I joined, so this is in 2022, so because of the way the security clearances work, I didn't really get to join the team until more or less right before this started, right? So it was in September 2022. Curiosity reaches this long-awaited salty region. So again, a place that had been mapped from space. We knew from the time the rover was launched that we're going to get to this salty region. About a decade after the rover lands, we're going to finally get to the salty region, and it's going to tell us something. We don't know exactly what, but it's thought, based on the amount of salt that is there, that this must represent the great drying of Mars, right? There's all of this salt being deposited because you're evaporating waters. So we were all very excited, and this, again, happens to be the exact part of the year that I joined the team. Okay, and so I joined two instrument teams on the rover right away. One of them was the ChemCam, again, this instrument that drives, or as the rover drives, it can stop and it fires this laser at rocks, turn it into a plasma. We take a picture of the plasma and we get a measurement of the chemistry of the rocks. Excellent reconnaissance. We don't have to unstow the arm. So this thing can basically go while we're driving, and it even has some automation so that we can stop driving automatically, and then it will detect rocks to blast with its laser. So as we're going, we notice something in the data from ChemCam. So you can see here, we're going, Canaima is the very beginning of this salty region. So these rocks that contain lots of salts as had been mapped from orbit. And eventually, we end up at this place called Topo Caparo. So Topo Caparo, you could see above Topo Caparo, so the rover in actuality is going south, right? Even though it's climbing the mountain, it's going south here. You can see that there's a transition in the color of these points. These points are just to show you how different the data are from one another, right? You can see that there's data above Topo Caparo here, all orange and or sorry, yellow and green, and then right at Topo Caparo, we transition to be this blue purpley color, suggesting that something very dramatic has changed between the data before Topo Caparo and the data after Topo Caparo. So really useful data is coming out of the ChemCam instrument, very reconnaissance based though. So we know something about the chemistry has changed, but we don't know exactly what and why. So something changed right there. Ultimately, what changed, which we learned by drilling into the sediments and putting those data or putting those samples into the rover and running them through the X-ray diffractometer instrument, is that these samples were full of carbonates. So they're full of this record of the ancient atmosphere that we've been searching for so long, that I, in 2017, knew so little about Mars, but knew enough to know that that's one of the big questions in trying to understand Mars. So again, these are pie charts. These are what scientists often use to show distributions of data as a function of the total amount. And you could see the amount of the pie here that's actually attributed to this iron carbonate mineral, siderite, is on the order of about 5 to 11%. So not a ton. If somebody gave you 5 to 11% of a pie, you wouldn't be particularly happy with that, right? You'd probably want closer to a quarter or more. But ultimately, that's what we see. And nowhere else on the entire planet had we ever observed that much carbonate in one place before. So this is an example of a time where we discovered something that we actually didn't expect to be there. This had been looked at from orbit, and we had no idea that it was going to be there, and it was actually masked in the signals, which we determined afterwards. And it actually turns out to be, if we sum over the entire planet, enough CO2 to actually give the atmosphere a pretty good kick in order to begin heating the planet, if you put all the CO2 back in the atmosphere. So we can use Gale Crater as an example for representative samples around the entire planet. Okay, so back to the scientific method here. So we did our prediction, Mars rocks should be full of carbonate minerals. And the result in this case is that lots of carbonates, but they were hiding from detection. So we looked in the orbital data, but they weren't there. Actually, because they co-occur with this magnesium sulfate salt, you actually cannot see the iron carbonates in that data. Folks have now looked, and they've done experiments in the lab to show that if you put those two minerals together, you only see one of them. You only see the sulfates. So actually, this stuff has been hiding in plain sight the whole time. It took having a rover on the ground with a drill and an X-ray diffractometer to determine that this mineral was actually there. And so the inference is the result. So this is the paper that Annie mentioned that came out last year. Carbonates identified by the Curiosity rover indicate a carbon cycle operated on ancient Mars. So we found carbonates in Gale Crater. There was a carbon cycle on ancient Mars. What's a carbon cycle? Okay. Carbon cycle for us is defined based on our understanding of the way Earth's carbon cycle works. So I'm not going to go into all of the details here, but you can see orange arrows going up. That's sources of CO2 to our atmosphere. If humans weren't combusting fossil fuels, the way CO2 mainly gets into the atmosphere is through volcanoes. Okay, and the same thing would have happened on Mars. I'm sure if you've been able to see the Olympus Mons exhibit over here, that CO2 coming out of these large volcanoes on ancient Mars would have been voluminous. It would have gone into the atmosphere. But on Earth, we have subduction. So actually, on Earth, whenever that CO2 goes into rocks, makes carbonate minerals like limestone, and gets subducted back into the Earth, it gets cooked off, and that CO2 goes back up into the atmosphere. So we have a cycle here on Earth that enables it. And so what is subduction? Basically, you can imagine everyone is familiar with Vancouver Island and the Cascadia subduction zones, particularly if you've been there and been through the earthquake drills. So effectively what's happening is that CO2 that gets locked up in the oceanic crust, limestones, carbonate reefs, stuff like that, actually dips down into the mantle and then comes back up through volcanoes. So Earth has been able to maintain habitability over geologic time because it has plate tectonics, right? CO2 comes out of the volcanoes, goes up into the atmosphere, becomes limestones, goes down into the mantle, and then comes right back out. So as time has gone on, as I said earlier, the sun 4.5 billion years ago was significantly less bright than it was today, about 30% less bright today. The sun has gotten brighter, And somehow the CO2 cycle, the carbon cycle on Earth has actually been able to keep lockstep so that it's been more or less about 25 degrees Celsius on the surface of Earth for 4 billion years, except for a few times where we became a snowball. Okay? But Mars, on the other hand, has no subduction. It does not have plate tectonics. So Mars actually lost most of its atmosphere by about 3 billion years ago. So this is a bit of a challenging diagram, but I show it because it does show exactly what I'm trying to say here. So Mars's atmosphere, you can see the line going, and then around 3 billion years or so ago, it goes away. Okay, Earth's atmosphere, more or less the same. It's gone up and down, but it's more or less the same through time. The surface age of Mars on the top there. So how much of the rocks on Mars are more than about 3 billion years old or so? Almost all of them. So the surface of Mars is what you had 3 billion years ago. So the rocks there more or less have not changed. We have no new rocks since about 3 billion years ago. Earth's average age of rocks are much younger. Most of our rocks are like on the order of 100 million years old or something like that. We have very few really, really old rocks here on Earth because plate tectonics is constantly subducting material and turning it back into new rocks, new volcanoes, new et cetera. Okay, so the Martian carbon cycle, which ultimately was required to keep Earth habitable, or Mars habitable 3.5 billion years ago, would have been imbalanced. So the idea is that we have CO2 coming from the atmosphere, going down into the rocks, and only a little teeny tiny bit of it will come back. And the little teeny tiny bit of it that will come back is actually through a completely separate process, nothing to do with subduction, but actually through the generation of really acidic brines on Mars. So these really acidic brines basically would have been like dropping acid on carbonates, which many geologists would have done in their field schools. When you drop the acid on the carbonates, it fizzes, that's CO2 going back into the atmosphere. So that would have been a really weak feedback. So the up arrow here is much weaker than the down arrow. So CO2 would have gone into the rocks and not come back out. So again, a schematic diagram of how that would have worked. Before about 3.5 billion years ago, Mars would have actually taken CO2 from the atmosphere into these waters, and then they would have been deposited as carbonate minerals like siderite, like we observed in Gale Crater, which ultimately would have more or less all stayed there. Some of it went back, CO2 went back into the atmosphere, but most of it would have stayed in the sediments. So this is a tale of two planets, right? One which has remained habitable for more or less all of its history, that's Earth, right? So we're here potentially toying with its habitability a bit with our current actions, but for more or less the last 4 billion years, Earth has been habitable and inhabited. Mars, on the other hand, as the sun was getting brighter, as it became much easier to warm Mars, Mars actually became such that it was sequestering most of its atmosphere into the rocks. And as the atmosphere went into the rocks, it didn't come back out, which means that even though it would have been easier, there's more heat coming into the planet from the sun, it would have been easier to heat the planet. In fact, it became much harder to do so because the CO2 in the atmosphere was going away. Okay, so again, over the 13 or so years of the mission now, we've been exploring. So these big discoveries were made in that magnesium sulfate bearing unit, which had been mapped from space, and which again, for the first 10 years of the mission, everyone was like, well, we're going to see something interesting there. And in fact, we were able to make huge discoveries once we got there. And as we've gone on, the rover has gotten older and dustier. So there's a picture that was taken on Sol 84, a selfie. Here's a picture that was taken on Sol 3303. You can see we're now, Sol is a Martian day. We're now on Sol 4789. And so over that time, the rover has gotten dustier, its joints have gotten achier, it's had less and less ability to do the measurements that we want, but it's still performing nominally, which means we're still able to do all of the science we want. It just might take a little bit of extra effort, a little bit of different planning to do so. And again, we've made massive discoveries, and some of them are just about to come out this year, which is very exciting. So the rover, 13 years young, is still going strong. And over that time, this is about how far we've gone. So here from the Seton Public Library in South Calgary, you can more or less drive to High River. That's how far Curiosity has gone. That's not very far, right? So over that time, we've driven about 36 kilometers not particularly far, but we've made all those discoveries, and we're excited to see where the future will take us. I want to point out before I wrap up here that teamwork makes the dream work. This is a picture of us in the south of France in 2023. All of these people obey by the rules of the road. So this is what governs our discussions, not only within our team, but also in presentations to the public. So everything that I've discussed with you today has been approved for public release. And we're still going strong. I've just gotten renewed for an additional 3 years on the mission. And I'm just wondering at this point, what surprises await. So thank you very much, and I'm happy to answer your questions.
Great. All right. Thank you so much, Ben, for that fantastic talk. What an absolute treat on a Thursday night. We're going to get to questions here in a second, but first, I need to know why on the day you found out you were part of the mission, you look so cranky.
Well, Annie, do you even have to ask?
No, I don't. You were teaching online. It was 2021.
Yeah, teaching during the pandemic was not fun for any of us.
No, that was a tough time.
Yes.
All right, so we are going to toss the mic out to you to ask questions. If you are online, you can send your questions to scievents@ucalgary.ca, and I get to read them to you. Okay, a couple in the chat. Well, maybe we'll start with one online because I already have them. So the first question online is, did Mars's atmosphere go away because the geodynamo stopped? What caused that? Could this all be reduced to how the planet is half the size with more surface area to mass, losing too much heat, magnetosphere failure, and solar stripping?
Wow, Annie. I don't know who this person is, but they seem to know their stuff. So yes, indeed. Mars it doesn't have the geodynamo that Earth does. It doesn't have a magnetic field. It does not shield itself very well from solar wind. So basically what happens all the time, and actually the MAVEN instrument, or MAVEN orbiter on Mars has been measuring this, is it's losing its atmosphere to space. So because it has much less gravity, its gravity is about a third of ours, and it has no magnetic field, its atmosphere just leaks off into space all the time. And so if you integrate backwards from today to 3.5, 4 billion years ago, you can calculate how much CO2 was more or less lost to space. And it's a lot, but it's not all of it. So it turns out that actually that has been part of the process and has been losing CO2 the whole time. But early on, there must have been CO2 there in the atmosphere, which ultimately went into the rocks. And we've calculated how much CO2 is in the rocks, and it is quite substantial in terms of an atmospheric partial pressure.
Wonderful. All right, I think we'll turn it to the audience here. If you have a question, please raise your hand and we will bring you a microphone. Yeah, don't be shy about the microphone. Alexis gets to get her exercise in for the day.
Why didn't the water on Mars freeze?
It did. It's not very popular to talk about freezing water on early Mars, but there's no question that it would have frozen. And indeed, I will just briefly show you this really cool picture here. So this place here, right to the right of where it says Topo Caparo, is known as Geddes Vallis. Massive carved valley. Something came down that valley that was able to move rocks that were bigger than people. So huge boulders must have been rolling down this valley. And that's how it got carved out like that. And one hypothesis for that is that there was a big glacier sitting up outside of the crater that all melted catastrophically. And as it was catastrophically melting, there was huge rivers pushing huge rocks down this valley. So it did freeze. The nice thing about Gale Crater, and another reason why it has this huge stack of sediments, is because it's at the equator, right? So you can imagine Mars has many issues in maintaining habitability, but one of it is the fact that it has a very strange orbit and it wobbles a lot in its orbit. So during parts of the time, even at the equator, you're actually facing away from the sun. So you can imagine that if if the crater was facing away from the sun, really cold, you freeze a nice big glacier at the top of the crater, but then slowly you rotate back into facing the sun at the equator, that all of that ice very quickly melts and then makes these massive blowout rivers. So many of us believe that there was substantial amounts of ice on the surface of Mars. So it did freeze.
So, like, why don't you have like fine water on it?
Excellent question. Because most of the water is gone. So there's two places it went. One is the same issue that was asked in the first question, just blew off into space. It's kind of interesting how that happens because hydrogen goes faster than oxygen. So the hydrogen's blowing off into space, the oxygen sticks around. And interestingly, part of the reason why the surface of Mars is red and it's only skin deep is that oxygen sticks around, right? So the oxygen stays and oxidizes those rocks on the surface of Mars to make them this rust, kind of like would happen on your bicycle chain. And so the other place that all the water went is into the rocks. So part of the evidence that we have that there was water on Mars is that there's rocks that have a bunch of water in their structure. So not in pore space, so not like an aquifer, but like actual minerals that have water as part of their chemical makeup.
Wonderful question. What I love about this talk is that each question leads to 7 more questions. I'll get, if anybody else has a question in the audience, you can raise your hand and we'll bring the mic to you. We'll start with just a question online here while we're getting the mic to you. So the next question is, what was the concentrations of iron carbonate generally? You showed percentage, but what are the kind of concentrations?
So that's actually on the next slide. So this is kind of a concentration. So these percentages are weight percents. So indeed, there's quite a lot of iron. There's something that I've sort of been a bit cheeky about. So you notice that all of these pies are mostly one white color that is meant to draw your eye away from it to the other more interesting stuff. But most of these rocks are actually amorphous. So something that we can't see in the mineralogical data at all. And so there's probably a bunch of other stuff in there that we don't really know. So we actually, in practice, have a really hard time attributing how much of the chemistry of our total rock is in a particular mineral because we don't really know the chemical composition of that amorphous material. We have an idea, we make estimates, but we don't really have a good idea for what like 60% of the sample is actually made out of. So the concentrations here, the weight percentages, 10.5%, that's precise, right? But we don't actually know much about how much of the total iron is in that mineral because we don't know what half the rock is made out of.
All right, we got a question in the audience.
Why is the sky on Mars orange if there's no atmosphere to reflect the color of the planet?
Ooh, great one. It's the same, sort of the same issue as I was discussing earlier, that Mars is now dry because of all of the dust in the atmosphere, right? So this dust is all brown red. It's basalt, oxidized basalt, like I was saying. It's a lot of oxygen in the atmosphere that's oxidizing rocks on the surface of Mars. And a lot of this dust is just caught in the atmosphere. And so it's reflecting this orange-brown color back as the sun shines through it.
Great question. Have we got some more in the audience? We'll get the mic to you. Yes, they're nice and close by. So we'll go straight to an audience question. You don't have to run. It's okay.
On that map that you have of the transition, you said it's moving south up the mountain.
Yep.
So why is it that the carbonates are deposited so early on at a higher elevation as opposed to lower down?
Very good question. This might be a bit deceiving because this is only showing from Kanaima, which was drilled in October 2022, 10 years after the mission started, downwards, right? So before Kanaima, the rover had gone something like 27 kilometers, right? So actually there's a lot of rocks up above here that were lower in the sedimentary stack. I guess it'd be easier to show you if we just look at the mountain really quickly. So Kanaima is right there where it says magnesium sulfate unit, but we had to drive all the way there first, right? So we don't know how much time. It's really hard to say how long it took to deposit these sediments, but it could have been on the order of hundreds of thousands or millions of years that we drove through before we got to Kanaima, right? So it isn't the youngest rocks. It's actually quite evolved. But you notice that the magnesium sulfate bearing unit is nowhere near the top of the mountain. Curiosity, unfortunately, will never make it to the top of the mountain, but at least the transitions that we've observed so far have gone from clearly warm and wet, rivers flowing into the crater, to cold and dry salt water being deposited.
And how deep do one of these like drill samples go?
They're about 40 millimeters.
About 40 mil. Okay,
We're so proud.
thank you.
It's really good. Okay, we'll do another one online here just as we're bringing the mic around. I know there's another question lurking. Yes. Our online question is, how does the NASA's MAVEN mission findings impact your area of research?
MAVEN is an amazing instrument, or mission, and amazing. Unfortunately, MAVEN doesn't seem to be doing so well right now. But so MAVEN has been historically useful for several reasons. One is that it's been able to tell us about this escape that I was just talking about, like how fast it's been able to measure how fast gas is escaping out of the top of the atmosphere. At the same time, we've learned things about the chemistry of the planet based on MAVEN's looking downwards onto the planet. And then lastly, one of the most useful things about all of the satellites that are roving around Mars is that they help us link our data back, right? So that data, because they're up there, we only have to shoot our signal up to the satellite, and the satellite then shoots it the rest of the way back to Earth.
Wonderful. All right. I think we have time for one or two more questions. So if you have any burning questions left, oh yes, I'm just blinded by the light. Please go ahead.
Do we know or have a theory why there's no plate tectonics on Mars?
I would say we don't know, because if we did, then we'd be telling fibs. But the idea is that something needed to start plate tectonics on Earth, and it didn't start on Mars. So there's lots of hypotheses, and I really don't want to try to list all of them. But part of what people believe is that part of what needs to happen is, like, you need to initiate a subduction zone to begin with, right? So folks from our department, for example, will say, well, what happened on Earth is actually we made granites, right? We had these igneous rocks that became evolved that are much lighter than basalts. And so through that, we were able to bring rocks down into the mantle because there's this density contrast. And Mars doesn't have granites. It has nothing like granites. There's some rocks that are rich in plagioclase, the mineral that makes up granites, but it's not the same. So part of it is potentially that. But you could turn that question right on its head, is like, does Earth have granites because it has plate tectonics, right? So like, it's a really challenging, it's a vexing question that a lot of really smart people are working on. So, yeah.
All right. Have we got one more question? Yes, we do. I know we could go all night, hey?
Thank you, Ben.
All right, go ahead.
So if Mars is currently geologically and biologically a dead planet, what specific scientific or strategic catalysts justify the pursuit of long-term human settlement? Some space exploration company is, yes, telling the normal people that, like, oh, we are going to Mars,
Yeah.
Mars, like Earth is going to die, something like that. Why? And how?
Yeah, no, I mean, I think, I guess from the scientific standpoint, you send people to Mars and you have an actual geologist on the ground, and you can probably do a lot more. It's kind of like having sent people to the moon. Having a geologist, this guy, Jack Schmidt, that went to the moon, really revolutionized our understanding of lunar geology. So there's part of it as an expertise on the ground. I'm not of the camp that thinks we should send people to Mars to do science, at least. You know, some people I'd be happy to see head off to Mars for different reasons. But I think that we could do a lot with what we know about rovers, and I think we could do a lot more quickly. So if the questions are scientific, I think it'd be nice to have a whole bunch of really tiny drones that were able to do this mineralogy stuff that we can do. Like, you know, they have their own little drill, right? And you can imagine doing that, you know, cheaply and all over the planet at once in a way that you could never do by trying to keep humans alive on the planet. So I think there's a lot to be considered. So people want to waste their money, you know, doing that, that's fine. But in my opinion, we can do a lot better science with the robot geologists that we have, or by bringing samples back from Mars to Earth. Yeah.
Wonderful. Okay, well, if I could get everyone to join me one more time in thanking Ben for this wonderful talk, please give him a round of applause. Thank you so, so much for joining us here tonight. We do have another EarthX talk coming up on March 17th. The topic of that one will also be around space, and actually we're going to be exploring the habitability of Venus. So please join us for that one. You can get updates by signing up for emails, or you can just keep checking back on our website. Thank you all very much for joining us here tonight, and I hope to see you at the next one. Have a wonderful evening. Good night.